Hi guys, so I wanted to post a quick video about the detail of how the presence of a dielectric and a capacitor affects the capacitance. Since we've been working on this in lab and you've been working on homework problems with this, etc. I just wanted to try and connect the dots a little bit and give you an argument for how an insulator, a dielectric, and the capacitor impacts the capacitance. So if you recall, um, the capacitance is equal to the amount of charge that that thing can hold per applied voltage. And if you remember, we looked at this for the parallel plate case, uh, and we would talk about if you imagine this in 3D, this thing has some area. The area of the plate times sigma, the charge density per area would give you uh, the charge, and the voltage we related to the electric field between the plates. Remember, integrating the electric field, you'd find that that's electric field times the distance. And for in between parallel plates, that electric field is equal to sigma over epsilon naught. And our sigmas would cancel, and this was how we got the expression for a parallel plate capacitor, that its capacitance is epsilon naught A over D. Now, what happens if you put a dielectric in here? Here's one way to think about it. You can imagine this is a material inserted in between the plates. So unlike a conductor, so in a conductor, the charges can move around. Now, in a dielectric, they can't move around. That's not to say there aren't charges there, but you can think of this in the kind of the cartoon they have in your book is as composed of like little cells. So you can think of the charge can get polarized. It can get pulled. So imagine, you have charged up your capacitor. So what would happen is that each little individual cell is going to get polarized inside the capacitor. So while up here, you would have field lines that are pointing between the plates. Here you would have that as well, and it's going to polarize the dielectric material. So you can think of this graphically as what you had before. So you just have your field lines pointing between the plates. And then you're adding to that, the effect of this polarization would be, it's like the same situation, except it would have a small net electric field that's pointing the other direction. So if you imagine, the field due to that, so what that's going to do is when you imagine the superposition of those two fields, you would be left with a field in between the plates that's reduced. So here, let me try and draw it. Same. The same number of arrows. So your default electric field, you have this polarization electric field that's pointing the opposite direction, and then the resultant electric field is less. Maybe I'll put it like this. It's less than the default. Now, we can think about what impact that has on the capacitance. We know that the electric field is in the denominator. So this, our capacitance expression, this thing, So the electric field, instead of it being sigma over epsilon naught, it's going to be sigma over r epsilon. And we know that that's the same thing as sigma over k epsilon naught. So you can see what happens is you end up with, going to cancel k epsilon naught a over d. So you can think of this modification of the capacitance. The capacitance has gone up because the electric field in between the plates is reduced, and it's reduced because there is a contribution that's going to be pointing in the other direction that's a consequence of that dielectric being polarized in between the plates. Um, so I just wanted to show you guys this because it's an argument, it's an explanation for a mechanism for how the capacitance is modified with the dielectric. And I think that that's useful just to see that in addition to the mathematical expression that you just uh, change by the capacitance by a factor of k, the dielectric constant. So hopefully this helps you visualize a way for how this how the capacitance is modified with the dielectric.